Good morning, students. Welcome to the class on advanced organic reagents. Today we will discuss phosphorus reagents. Phosphorus reagents are a very important reagents used in many functional group transformations in organic chemistry. We will start one by one. Phosphorus reagents are used for desulfonation when it is treated with triethoxyphosphine. When it is treated with triethoxyphosphine, then desulfonation is possible. It is a stereospecific syn elimination reaction where if the two substituents are trans to each other, then alkene will be trans. So it is a stereospecific syn elimination reaction. If the two substituents are cis, product will be Z double bond, Z alkene. If the two substituents are trans to each other, product will be E alkene. A small variation in this is dehydroxylation of diols, 1,2-diols. How can we eliminate these two diols and generate a double bond here? We can dehydroxylate these two diols by first converting it into a thioester, C double bond S, C double bond S. We need to convert this into a thioester first, then we can treat it with the triethoxyphosphine so that we will get dehydroxylation. So these two alcohols will be removed and we will get a double bond. As I said, it is a stereospecific syn elimination. These two hydroxyl groups are trans to each other. So that means the double bond will be trans. 1, 2, 3, 4, 5, 6, 7, 8. We can also write like this. We can also write like this. This reaction is called as Corey-Winter olefination. Corey-Winter olefination. This is called as Corey-Winter olefination. To convert dihydroxy 1,2-diols to thioesters, generally we will treat this with This is called TCID. TCID means thiocarbonyl diimidazole. The beauty of this reagent is these two imidazole groups are good leaving groups. These two imidazoles are good leaving groups. That means we can easily convert 1,2-diols to thioesters using this reagent. Not only this, we can also use this reagent. In this molecule, we have 1,2-diol. So what we can do, we can convert this into an alkene. We can convert this 1,2-diol to an alkene when it is treated with in this case, it is the phosphorus reagent. Core-winter olefination is a stereospecific syn elimination. So, based on the stereochemistry of the diol, the alkene stereochemistry will depend. In this case, it is a syn diol. It is a syn diol. So, whatever the zigzag fashion, it will be retained here. We will get E double bond. When it is anti-diol, when it is anti-diol, then stereochemistry must be reversed. So here it is in zigzag fashion. We will get opposite stereochemistry. So that is why we will get Z double bond here. This is syn diol. So whatever the zigzag fashion is there, we will get the same stereochemistry. But when we have anti-diol, we need to change this. So that is why we will get cis double bond. So this is a stereospecific syn elimination. Now we will look at the mechanism. 1,2-diol first will be converted to thioester. Then we are treating with triethoxyphosphine. Triethoxyphosphine with its lone pair, it acts as a nucleophile. So it attacks on sulfur. Then carbon-sulfur bond will be polarized towards carbon. Since it has used its lone pair, it gets positive charge. Carbon is getting bond pair of electrons, so it gains negative charge. Then again, carbon negative charge will attack on phosphorus, so it generates a three-membered ring. It generates a three-membered ring. Of course, phosphorus can form 5 bonds, right? Nitrogen can form only 3 bonds, but phosphorus will form 5 bonds. Now this will undergo decomposition in such a way the sulfur will be forming a double bond with phosphorus, and this is generating a carbene. It is generating a carbene, and this sulfur is removed here, and we have generated a carbene. Again, one more triethoxyphosphine will add to carbene. So carbene is electrophilic in nature. Phosphorus with its lone pair will add to carbene as a nucleophile. So carbon uses its lone pair, so it gets positive charge, and it is donating its lone pair to the carbene, so carbene gains negative charge. Now at this stage, it will undergo decomposition. Negative charge will be polarized towards oxygen so that it generates carbon oxygen double bond. Then this carbon oxygen double bond will break down, so it will generate a carbon carbon double bond. Then this bond pair will be polarized towards oxygen, so it gets negative charge. This is how we will generate alkene from diol using desulfurization method or Poree-Winter olefination. Of course, this is not stable. This will again decompose. So it generates carbon dioxide plus triethoxyphosphine again. This is the overall mechanism for Poree-Winter olefination.